Hello, in this video we are going to continue our exploration of systems of linear equations with two variables. The previous video we talked about solving these systems of linear equations using substitution, and in this video we're going to move on and look at examples of elimination and graphing as to help us solve. So just to recap a little bit, when we want to solve the system of equation, we pretty much have like three options that we've been working with. Substitution was one option, elimination, and graphing are the other two. And that elimination and that graphing is what we're going to focus on in this video. So let's look at an example. In this example, they want us to solve the system and they want us to use elimination. So we're only going to focus on elimination. Granted, could you use substitution or graphing? Absolutely. We just want to show that example of elimination. So when I look at my system, I have two variables, x's and y's, or x and y. When I know these are going to be linear equations, when I look at my degree on my variables, my degree is 1, which is telling me that these are linear equations. So when we solve by elimination, we want to eliminate one of the variables. So when I look at my system, I either want to start off by eliminating my x's or I want to start off by eliminating my y's. And again, this is a personal choice if you want to do x's or y's. For this example, ultimately when I go to eliminate it, I really want my x's and my y's to have opposite signs, or these two x's to have opposite signs, or the y's to have an opposite sign. So I'm actually going to work on this problem by eliminating my x's. That's what I want to eliminate. So when I look at my problem, I can see that I have 2x and negative 4x. So I want those to be opposite of each other. So ultimately, on my top equation, I really want that to be a 4x. Granted, I could change the bottom function, or the bottom equation. I could change that into a negative 2x, but that means I have to divide everything by 2. I'm going to have a fraction here, and for some reason some of you guys aren't big fans of fractions, even though they are our friend. So ultimately, to start this problem off, I know that I'm going to multiply the whole entire top by 2. And remember, when it comes to multiplying things in equations, whatever we do to one side, we have to do to the other. So that 2 has to be multiplied through everything. So I just kind of throw some generic little parentheses around it and put the 2 out front to remind me that I have to multiply everything by 2. So I'm just going to shoot it over here. So if I multiply everything by 2, I'm now going to have what? 4x plus 8y equals 28, right? And then I'm just going to shoot this guy over and rewrite him. So negative 4x plus y equals negative 10. So now when I look at these two equations, I'm actually going to add these two equations together. So when I actually add these two equations together, what's going to happen? My x's are going to cancel out, right? Now I have 8y plus y, which is going to give me a total of 9y's. And that's going to equal 18. Divide by 9, and y equals 2. On my system of equations, I know that these are lines, and I know that I'm looking for where those lines intersect. So they would intersect at a point. So here's my y-coordinate, so I need to figure out what my x-coordinate's going to be. So now that I have y, I'm just going to plug that into one of the two original equations. And it doesn't matter which one you pick. You can either pick the first one or the second one. And I'm just going to go ahead and pick the second one. So we had negative 4x plus y equals negative 10. But we just solved that y equals 2, so I'm going to take that and plug it in for y. So negative 4x plus 2 equals negative 10. Negative 4x equals negative 12, just doing some algebra, and then I'm going to get x equals 3. So my system of equation, the solving it is going to be a point, and it's going to be at the point 3, 2. So let's spice it up a little bit. Same thing, we're going to solve the system, and again we're going to solve just using elimination, just as for sheer demonstration purposes. You can pick if you want to do substitution or graphing. We're going to do elimination, right? So I'm going to look at my two equations and I need to make a decision. Do I want to eliminate my x's or do I want to eliminate my y's? And just for the fun of it, I'm going to say that I want to eliminate my y's. So if I want to eliminate my y's, I have a positive 10y and a positive 5y. So if I have 10y's, I need to subtract 10y's in order to get rid of it. So again, I could go through and divide by 2, which would be perfectly acceptable, and actually fairly easy considering they are all even numbers. But I'm just going to go ahead and multiply my bottom equation by -2. So I'm just going to throw some generic parentheses out there. I'm going to put that -2 out front just to remind myself to make sure I need to multiply everything by -2. I'm going to just take my top equation over just so I can keep everything in a nice little linear fashion when it comes to doing some algebra. So I have 18x plus 10y equals 4. And when I go through and I multiply by -2, I get -18x minus 10y equals a positive 6. So now I'm just going to do some algebra, right? 18x minus 18x gives me 0. 10y minus 10y gives me 0. So I have 0 on the left, and that's going to equal 10. And does 0 equal 10? No. So we know that this is never true, right? So this is giving us an example of no solution. And what does it mean if we want to solve a system of equations and it has no solution? Well, our solution is where our lines cross, so this is ultimately telling me that my lines are not going to cross. So what kind of lines do we have that will never cross? Parallel lines. So this is actually an example of parallel lines. So with some practice of solving by elimination, it does take a little bit of practice to get used to it, and it's pretty doable. The last example we want to go through is where we are solving our systems of equations, and we're using graphs in order to come up with our solutions. So on this example, we have two equations. When I look at these two equations, I can tell that they are going to be linear equations. Again, my highest exponent is 1, so that's telling me that it's linear. And even on these examples, it was very kind of them. They gave us examples that are in that slope-intercept form. So we know the y-intercept and we know the slope. So these two are fairly easy to graph, doing them by hand and not having to necessarily use a graphing calculator. So I'm going to try this first time making graphs on my little iPad with my stylist, so let's see how well this turns out. So if I go to graph my top equation, I know that my y-intercept is at 4, so 1, 2, 3, 4, right? And my slope is 2/3. Well, from this point, if I go up 2 and if I go a positive 2 and a positive 3, I'm going to be off my graph. I'm going to be somewhere up in here, which is not going to be very accurate. So even though I went positive 2 up and positive 2 to the right, because my slope is positive, I can actually do that the same thing as by going down 2 and left 2, right? A negative over a negative is the same thing as a positive. So from 4, I'm going to go down 2 into the left 3, and I get this point. Any 2 points make a line, so I have 2 points to where I can make my fancy little line. Then to graph the second one, same philosophy, right? In my blue line, my y equals 2/3 x plus 4, even by going down 2 and left 2, I still have that positive slope, right? Double check yourself. This is a positive slope. Is this a positive slope? Yep. So hopefully we graphed it correctly. So now let's look at our second one. So our y-intercept is at -3. Our slope is -5/3. And again, if I go down 5 and to the right 3, I'm somewhere over here, and it's not very accurate. So I can do it instead of my change in y being negative and my change of x being positive, I'm going to do it just the opposite way. And I'm going to say that my change in y was positive, so 1, 2, 3, 4, 5, and my change in x was negative, 1, 2, 3. And then now I'm going to attempt to draw that perfect line? Well, use your imagination, right? That's what we always say. So ultimately, when it comes to finding our solution to our systems of equations, we're looking for where our two lines intersect. And where do our two lines intersect? They intersect at that point, -3, 2. Real quick, I'm kind of making this video a little long. If you were to do this in a graphing calculator, you can put this, this is your y1, this is your y2. You can hit graph and you can see it on the graph. The other option is to hit that second graph button, which will actually give you a table. And when you pull up the table, it'll say x, y1, and y2. And ultimately, this is your x points, coordinates, right? And then y1 is that first function you put in. So this would probably be your y1 and this would be your y2. And then it's going to list all of the results. And just like if we just sat there and did -4, -3, -2, right? This ends up being like repeating 0.6. This is 5.3 repeating. This is a 2 and a 2. This is 2.6 repeating. Sorry for the penmanship. This is 0.3 repeating, right? -1, 0, even at 0, I think it's the 0.4, -3, right? So ultimately, though, we want to find where these two intersect, these two lines intersect. So they're going to intersect where their x and their y value are exactly the same. So here, my y values are different, my y values are different, my y values are different. But if I look right here, my y values are the same, and they're the same when my x is -3, and that's telling me that point, -3, 2. So that's where they intersect. So you have an option. You can sit there and sometimes you can see it right on the graph, other times if you go to the table, and we'll get the same answer. I hope this was helpful. If you guys have any questions, please reach out to me, ask questions. Have a good day. Talk to you later. Bye.